Good evening students, welcome back. So today we are going to discuss something about transition, inner transition and coordination compounds. Of course, all are interlinked, that is the reason why we have merged all these chapters and we are going to discuss all the previous chapters, the questions that have appeared from these chapters, transition, inner transition and the coordination chemistry, which is the I can say the most important part of the JEE from the inorganic perspective. Okay, let us start our discussion with the past papers. Let us starting with the multiple choice questions with one correct answer, right. So, this is the one what we are going to take up for almost 4 to 5 questions. Let us solve in that way, where one question is the one answer is the right. Let us start the question. Which of the following combination will produce hydrogen gas? That means you have been given with the metals as well as with the acids also. Okay, not all the acids when reacted with metals produces hydrogen gas. Okay, but again I am reminding you, this question contains only one correct option. So, guess the students, what is the right answer? What do you think? When iron metal reacts with concentrated nitric acid, what is the product form? When iron reacts with nitric acid, do you think hydrogen gas is liberated? Or what happens when copper is treated with nitric acid and zinc with sodium hydroxide, aurum, that is gold, treated with sodium cyanide in the presence of air? In the presence of air, it can be oxygen, it can be moisture, that is water vapor. So, does it produce hydrogen gas? Okay, so right guys, you are giving A as the answer. Okay, let us see the answer and we will also see what happens if A reacts or B reacts or C reacts. What are the byproducts formed, whether the hydrogen gas is liberated or not. Let us see. So, okay, I have here, when zinc is added to concentrated sodium hydroxide, then you get the compound sodium zinc oxide. But see, here there is liberation of hydrogen gas, but what is going to happen when iron or copper is treated with nitric acid? This is water that is liberated, it is not the hydrogen gas. Got it? The nitric acid, water is liberated. That means the iron metal or the copper metal is liberating the water, it is not the hydrogen gas. Is it clear? Yeah, gold is noble metal, yes, you are right. So, that is the reason why in the presence of sodium cyanide, that is oxygen and water, where you get sodium dicyanoaurate. You can refer back to your knowledge on IUPAC of the coordination compounds. Here there is liberation of hydrogen peroxide, it is not the water again. Is it clear to you? In the first one here, the zinc is treated with sodium hydroxide, is liberating you hydrogen gas, that is metal with the base, that is what we know, right. All the times exceptions are the one which are quite important, and here also you are coming across one such question, whereas here these two metals are liberating water and the gold is liberating hydrogen peroxide. So, the correct option for this is C. Moving on to the next question. Yeah, I just kept the periodic table for your reference for this question. Look at this question. Now you will understand what is the purpose of keeping the periodic table here. Okay, geometries of the ammonia complexes of nickel, platinum and zinc. Okay, so we have three things here. Ammonia complexes, please note on this. The ligand is ammonia, whereas the central metal atom we have three things: nickel, platinum and zinc. What they are asking is, when nickel, that is the central metal atom, is binding with the ligand, that is the ammonia ligand, what is going to be the geometries? Is it octahedral, square planar and tetrahedral, square planar, octahedral and tetrahedral, tetrahedral, square planar and octahedral, and vice versa? So it is rotating again. But here one tricky thing and one easiest thing is, if you find out one, it is easy to trace out. At least you can be eliminated with few more options. One more tricky thing is, they have chosen ammonia as a ligand. Yes, that is what I am saying you, Pardo, metal plus acid, hydrogen gas, right? That is what I am saying you, there are exceptions, like the acid what I have chosen, nitric acid, right? Okay, look at this. Here the geometries, when we are speaking about nickel, platinum and zinc, and the ligand what was chosen, can I have a question for all of you? Can you tell me ammonia is a strong field ligand or a weak field ligand? Ammonia, is it a strong field or a weak field ligand? In the spectrochemical series, all the ligands are classified as the strong field and the weak field, but what happens to ammonia? Ammonia is going to be a moderate ligand. It cannot be too strong, not too weak. So how to decide whether ammonia is a weak field or a strong field? Yes, exactly, I am coming to that. Usually we will take ammonia by default at a strong field ligand, right? So Madan, Atharva, all of you are answering me that ammonia is a strong field ligand. But if you look at the spectrochemical series, oh yeah, I have a spectrochemical series for you. Ammonia is present over here moderately. Okay, it can be a strong field ligand, it can be a weak field ligand. It is that this is one exception. That is what I have said you in the previous questions also. You will get the questions on the exceptions. Ammonia is such an exception. Most of the times we consider ammonia as a strong field ligand, yes. But when we consider the ammonia as a weak field ligand, it depends upon the oxidation state, the central metal atom, right? The oxidation state and the central metal atom. For example, let us see. I have a ammonia, right? Here this is ammonia. Now whether it is strong or weak, if it has a coordination number 6 or if it has a coordination number of 4, then if the metal is of 3D series, if the metal, the central metal atom is from the 3D series, or the central metal atom can be 4D series, or the central atom can be from 5D series. If the central metal atom is from either 4D series or 5D series, then ammonia is a strong field ligand. Ammonia is a strong field ligand. But if the central metal atom is from the 3D series, sure Pardo, I will show it to you. Right, you can have a look at this. You can have a look at this, the spectrochemical series, right? If the 3D series, if you have a ammonia whose coordination number is 6 and here whose coordination number is 4, then here it has a strong field ligand, here it acts as a weak field ligand. So ammonia cannot be judged as either strong field or weak field completely. It depends upon the coordination number, oxidation state of the central metal atom and even the geometries also. So this is something which you have to remember. Okay, look at this. Now you have nickel, platinum, zinc as the central metal atoms. So in platinum I can say directly that ammonia is a strong field ligand. What does a strong field ligand does? Whether it pairs up the electrons or it cannot pair up the electrons. I am just taking it directly, nickel and zinc, leaving it apart. Okay, don't consider nickel and zinc, because in the 3D series the ammonia complex has some exceptions, whether to consider it as a strong field or a weak field. But if you consider the platinum, which belongs to a 5D series, it is always, the ammonia is always a strong field ligand. Now take the hybridization of this one, right, find out the geometry of this one, so that we will try to answer this. Now what happens, as it is a strong field ligand, whether it pairs up or it cannot pair up the electrons. It, strong field ligand, pairs up the electrons. Strong field ligand always they pairs up the electrons, right. Now look at the platinum, where is it? You have a platinum over here, platinum plus 2, right. Now 4s2, sorry, here it will be 6s2 electrons will be lost, you will be left with, you have the hybridization. Now look at this, here you will have a square planar, you will have a square planar shape. So where does a square planar comes up? You can see square planar, here also it is a square planar, these two cases. Got it, guys? Is that clear to you, whatever has been taught to you so far? I have a question for you again. Can you tell me when it is called as tetrahedral, when can it called as square planar? If you have a ligand, say you have a central atom associated with the ligands. Now you have 4 ligands associated with the one central metal atom. Can you tell me what the geometry can be? The geometry can be the two possibilities, right? One with 4, that means I am writing here, if the coordination number is 4, then there are two possibilities. One, it can be square planar and it can be tetrahedral. It can be either square planar or tetrahedral. Got it? Very good. Yeah, if it is square planar, it is dsp2 hybridization, here it is sp3 hybridization. This is one thing which you have to remember. Square planar has dsp2 hybridization and tetrahedral will be having sp3 hybridization. So based upon this you can find out the geometries. Okay. Okay, look at this. Among nickel carbonyl you have 4, NaCl4, CONH3 and ClNa3COF6. Here you have Na2O2 and CS2. Now the question is, how many number of unpaired electrons, or I can say paramagnetic compounds, number of paramagnetic compounds. So I will give a minute, just find out how many number of paramagnetic compounds are. Total number of, you have 6 coordination compounds, out of 6 how many are paramagnetic in behavior? Yes, someone is asking you, someone is asking how can I say coordination number? Coordination number is nothing but number of ligands attached to a central metal atom, right? Number of ligands that are attached to a central metal atom, that is called as coordination number. Okay. So what is your answer? How do you find out the number of unpaired electrons? Number of unpaired electrons. See, here paramagnetism. You can say any number of odd number of electrons. Odd number of electrons are always paramagnetic in behavior. Apart from that, the electrons with 10 electrons and 16 electrons, they are also paramagnetic in nature. Three things: odd electrons, which are nothing but unpaired electrons, 10 electron species, though they are paired up, 10 electron species and 16 electron species. These are always paramagnetic in behavior. Based upon the bond order, you can also remember all the bond orders with the fractions. Bond order with fractions are also paramagnetic in behavior, right? Look at this. So, I have a number of compounds are 3. What are those? Here, these 3. So, how did you find out whether these compounds are paramagnetic? As I told you, you need to find out the number of unpaired electrons as well as here these 3 things you need to know. The sum of electrons must be odd due to presence of unpaired electrons in an element, and the bond order, which is nothing but it should be fractional. The bond order should be fractional. Based on this, we can find out the number of unpaired electrons, which is nothing but those compounds are paramagnetic in nature. It's clear? Moving on to the next question from JEE Advanced 2014. Look at this question. Match each coordination compound in list 1 with an appropriate pair of characteristics from list 2 and select the correct answer using the code given below the list. So, what is the list given to you? Okay, they are asking something about whether they are paramagnetic or diamagnetic or what kind of isomerism they exhibit. So, this is something related to apart from finding out the number of electrons, you need to know the isomerism also, the structural isomerism and the stereoisomerism, right? We will look into it. The first one, chromium, you have NH3 4 Cl2 Cl. Then Ti, that is titanium, you have 5 aqua, then chlorine and NO3. Platinum, you have ethylene diamine, En is ethylene diamine again, ammonia, chlorine and NO3 group. Here also you have CO, NH3, NO3 2 and NO3 outside. So, here they are asking you the paramagnetism and exhibits ionization isomerism, diamagnetism cis trans, paramagnetism cis trans, diamagnetism ionization. So, you have like a very difficult way to eliminate the options first of all, because you have a paramagnetism and ionization isomerism. Here you have diamagnetism and exhibits ionization, and in this also you have paramagnetism with cis trans, diamagnetism with cis trans. How do you find out? Firstly, tell me, how do you find out whether it is a cis trans isomerism or not? How do you find out the cis trans? Right, here find out the number of ligands that are present. How many ligands you have, whether it is octahedral or the square planar, right? Okay, of course you have the codes here, like in order to pick up the options also. I am skipping it off, showing you this one. Here the chromium, the central metal atom, if you see, that means if you find out the oxidation state, of course ammonia, which is a neutral ligand, with Cls, you have 3 Cl, so Cr plus 3 is having D3. Find out the number of unpaired electrons, D3. 3 unpaired electrons, it is paramagnetism. It shows cis trans isomerism. It shows cis trans, why? Because you can see the chromium with number of ligands. Here as well in titanium, if you look at this one is 0, here is 0, with the Cl you have D1, Ti plus 3. Got it? Ti plus 3, 3 unpaired electrons, paramagnetism, ionization isomerism. Ionization isomerism because of this NO3, NO3 which is present outside the sphere, coordination sphere. In the platinum ethylene diamine you have ammonia, chlorine, NO. So here platinum is plus 2 and it is having D8. Here this complex is square planar because the electrons are paired up. You can see here platinum is present in the 4D or 5D series, where in which it's not platinum is not in the 3D series. So here the ammonia ligand is a strong field ligand, it pairs up the electrons and it behaves as a, the geometry is square planar, so it exhibits ionization isomerism. Got it? The next one you have cobalt, which is having D6 isomerism, sorry D6, that is 6 unpaired electrons, and if you pair it up you have 1 paired and 4 unpaired electrons, which is nothing but cis trans isomerism. So the options, if you look at it, the answer will be B. So this is also the question from Advanced 2014. So far we have seen the options with one correct answer. We have seen the questions with one correct answer. Now we are going to watch the multiple choice questions with one or more than one correct answer. Okay, yeah, here you have some interesting question. Addition of excess aqueous ammonia. I am highlighting it because this is the one thing which you need to keep in mind in order to answer this question. Addition of excess aqueous ammonia to a pink colored aqueous solution of MCl2 6H2O. Okay, this is some compound that is given to us, say that is as X, and ammonium chloride gives an octahedral complex Y. So in the presence of air, so in aqueous solution the complex Y behaves as 1:3 electrolyte. Okay, what is Y here? Y is an octahedral complex. The reaction of X with excess hydrochloric acid, here the reaction of X with excess hydrochloric acid at room temperature results in the formation of a blue colored compound. Okay, so we need to frame the reactions, I will show it to you. So the calculated spin only magnetic moment of X and Z is 3.87 Bohr magnetons, it is given, whereas it is 0 for complex Y. Now what you need to find out? What are we going to find out here? Among the following options, which statement is correct? Remember, for this question there are more than one correct answer. What are the statements given to you? The hybridization of the central metal ion Y is D2sp3. Okay, should I consider this or not? We have to consider it. Why? Because look at this, Y is a octahedral complex. So when we say it is an octahedral complex, it can be either sp3d2 or d2sp3. So whether it is sp3d2 or not, or whether it is d2sp3 or not, we need to cross check, right? We cannot eliminate this option directly. Z is a tetrahedral complex. Again, so where the Z is formed here? Here. That means X, this compound, that is MCl2, MCl2, when reacts with excess HCl, you will get Z. The geometry of Z is square planar, they are saying. So, whether it is square planar or not, again we need to check. Addition of silver nitrate to Y gives only 2 equivalents of silver chloride. When X and Z are in equilibrium at 0 degrees, the color of the solution is pink. Okay, let us write down what was given in the question. X, which is pink colored, when reacted with ammonia, that is excess ammonia, in the presence of A, you get a Y. The shape of the Y or the geometry of the Y is octahedral. Okay, this part was given and this part also was given in the question, that is room temperature, whereas in excess HCl when you are adding, you get a Z, that is a blue colored compound. Here you are saying aqueous solution, wherein which it is a 1:3 ratio of the electrolyte. So, what is going to happen? This part you can see magnetic moment is 3.87 for compound X and Z. This one is Z and for X. Find out the oxidation state of the central metal atom. Where is the cobalt here? You have cobalt whose atomic number is 27. Oxidation state, that means see cobalt with 6 aqua, that is water and chlorine. So, aqua is neutral, that means it does not have any oxidation state, whereas chlorine, which is having -1, the cobalt oxidation state is +2. Cobalt oxidation state is +2 here, which means if you find out the geometry with the how many number of unpaired electrons, +2, in the sense you have 1, 2, 3, 4, 5, 6, 7, right. So, it is going to pair up, then it has sp3d2, has sp3d2 hybridization, got it. But what was given here? The hybridization of central metal atom is d2sp3, so A is not an option. Is it clear to you? Next, you have Y, wherein which oxidation state of Y is +3 here. Of course, you have presence of 3 chlorines. Because how is Y added? X when treated, that means ammonia, you get a Y. That is what. Here the water molecules are replaced with ammonia when you are treating with excess ammonia, right. So, the oxidation state is going to be +3 here. So, Y is d2sp3. The hybridization of central metal atom in Y, sorry, this should be correct answer. For X it is sp3d2, for Y it is d2sp3. So, option A can be considered if it is for Y. If it is for X, this option has to be rejected. Here Z compound which is formed is COCl4. What is COCl4? The shape is square planar, yes. Look at this, CO, you have Cl, right. This gives you a square planar shape, CO, cobalt. Okay, it is not the tetrahedral, you can work on the electronic configuration and check it out. So, these are the 2 correct options. What are those? The first one and the second one, where the Z is having a tetrahedral complex, right. The next one, the correct statement about Cr2 plus and Mn3 plus. The atomic numbers of chromium is 24 and manganese is 25. So, look at the options here A, B, C, D. Cr2 plus is a reducing agent, Mn3 plus is a oxidizing agent. Both Cr2 plus and Mn3 plus exhibits D4 electronic configuration. When Cr2 plus is used as a reducing agent, the chromium ion attains D5 electronic configuration. So, this is something which we have to work on it, right. Give me your answer. What do you think the answer can be? Multiple answers. Where is chromium and manganese located? I have my chromium here, manganese here. They are saying Cr2 plus and Mn3 plus. Yeah, this can be Cr2 plus Mn3 plus. Cr2 plus or Mn3 plus can attain the same sort of configuration. Of course, 4s2 is gone in both the cases, and one more electron from D leads the same configuration. But we need to check whether they have how many, whether they have D4 electronic configuration or not. That is what we need to see. Then, so loss of 2 electrons, so it leads 1, 2, 3, 4. Yes, here also manganese attains here, it also has 4 electrons. That is D4 electronic configuration. That means option C is correct. What about these two options? Cr2 plus Mn3 plus. What happens? What is going to happen? Cr2 plus Mn3 plus, when they are reacted, you can see that chromium is losing an electron, whereas manganese is gaining an electron, which means chromium is acting as a reducing agent. It is losing an electron, it is acting as a reducing agent, whereas manganese plus 3 is an oxidizing agent. And of course, they both exhibits D4 electronic configuration. You can see 1, 2, 3, 4. Upon splitting, you can see here T2Z3 and EZ1. So, the options can be, the answers can be here: A, which is a reducing agent, B, oxidizing agent, and they both have D4 electronic configuration. These three are the answers. Okay, Fe3 plus is reduced to Fe2 plus by using hydrogen peroxide in presence of sodium hydroxide. Okay, sodium peroxide, this is right, it is sodium peroxide in water, hydrogen peroxide in presence of sulfuric acid, and sodium peroxide in presence of sulfuric acid. Okay, so here two things, one is hydrogen peroxide and sodium peroxide in presence of sodium hydroxide. Here also you can see sulfuric acid, and this is in water. When it can be reduced to Fe3 plus to Fe2 plus. Yeah, Pardu, you should know the splitting of orbitals. Yeah, this is a crystal field splitting, you should know about that, because splitting of orbitals is something where you should know it better based upon the type of ligands that are present, whether it is strong field ligand or a weak field ligand that is associated. Okay, splitting generally happens. For example, you all know what do you mean by degenerated orbitals. Okay, if I say degenerate orbitals, means d orbitals has same energy like this, right? This is how d orbitals looks. But this is of what? Central metal atom. Metal atoms, d orbitals. If a ligand is approaching, okay, if a ligand is approaching these, the energy disturbances takes place in the d orbitals. Usually they all have same energy. When if you take a nickel or platinum or palladium, whatever it is, they have having same energy, which we call as degenerated d orbitals. When a ligand is approaching these d orbitals, then the energy differences takes place, which causes splitting. Got it? The depth of the splitting, the energy differences between the splitting will depend upon the type of ligand, whether it is a strong field ligand or a weak field ligand. Is it clear? So here the answers can be both A and B, because see, Fe3 plus is reduced to Fe2 plus in the presence of hydrogen peroxide. One more thing is here, sodium peroxide and water also is giving you hydrogen peroxide and sodium hydroxide. So here in these two cases, here also you can say that Fe3 plus can give you Fe2 plus. So, answers can be these two in water. Okay. So, this is something regarding the isomerism. The pair of coordination complex or ions exhibiting the same kind of isomerism, they exhibit same kind of isomerism. That means the two pairs, what are the two pairs exhibit the same kind of isomerism? Okay. So, we have chromium, ammonia, chlorine and chromium, ammonia. So, here this one is remaining same, everything is same, but you can see here it is 5, this is 4, right. You need to observe this one, because if you forgot that saying that this is also 5, this is also 5, interchange of this one, yes, definitely it leads to isomerism. But Cl2 is in the sphere, whereas Cl is outside the sphere in this case, but if you look at the number of ammonia molecules, here it is 4, but here it is 5. It is not a isomerism at all. Next, you have cobalt, ammonia 4 and Cl2 plus, platinum as a central metal atom. Yeah, here 2 ammonia, number of ligands here are 6, here you have 2, then 3, 4. Okay, we can think of this because this can be octahedral and this can be square planar. If you see cis trans isomerism, okay, if you consider about cis trans isomerism, this can be octahedral, this can be square planar. The chances are there. Let us look at the structures as well. Here also you have CuO Br2Cl2 and platinum Br2Cl2. Chances of isomerism again. So, you have here platinum ammonia and yeah, look at these structures. If you look at the structures, okay, I have the answers like saying B, C, B, D, okay. My answers are B and D. So, B anyway, that is what I told you, octahedral complex, square planar complex, they show geometric isomerism, this is cis trans isomerism. Again here in the D, because of this they exhibit ionization isomerism. Okay, see here the central metal atom is different, moreover you have the charge differences present. So, B and D can exhibit same kind of isomerisms. The next method of questions what I am going to discuss is the subjective problems. Of course, you do not have any options, that you need to find out. The number of geometric isomers possible for the complex COL2, this is capital L, that is ligand actually, L2Cl2. So, what is L here? Why it is named as L2? Because it is a bidentate ligand. It is a bidentate ligand, when which the lone pair of electrons on the nitrogen as well as the oxygen both can act as a electron donors to the central metal atom. That is the reason why we are referring it as a bidentate ligand. So, the L is here this one. Okay. So, how many compound, that means how many number of geometrical isomers, that means they have given it directly saying that okay, this complex exhibit geometric isomerism. CO, you have L, right, then Cl, bidentate ligand again, yeah. This way you can see the central geometrical isomerism which is M AB2, AB2 type here because you have this one. Then C2, total possible geometrical isomers are 5. This is the combinations, how many different number of combinations we are representing. You can this. So, AB is my bidentate ligand. So, one is a NH2 and oxygen, that is O minus and lone pair of electrons on the oxygen, right, this one, and C is your this one chlorine, this is Cl, this is Cl. There are 2 L2s, so one is this L, other is this one. So, this is the different number of possible ways we are writing it. So, here I can come up with 5 geometrical isomers. Okay, this is something which is different. Okay, right. In the complex acetyl bromido dicarbonyl bis, remember this, bis triethyl phosphine iron 3, the number of FPC bonds are, how many number of iron carbon bonds are present. So, high pack nomenclature of the coordination compounds is necessary in order to solve this question. How do you go with this? This is the structure. So, you have an iron, the central metal atom, the number of bonds that are directly bonded, FEC bonds, it is not FeCO bonds, okay. Iron directly bonded to one carbon, second carbon and third carbon. So, here you have FeC bonds is 3. You need to know the nomenclature from the name to structure and structure to name is very much important to know, right. Okay. Among the complex ions, so this is something tricky where 1, 2, 3, 4, 5, 6 complexes are given, the number of complex ions that exhibit cis-trans isomerism. Think about it, what will be the answer? What is your answer? The number of complex compounds that exhibit cis-trans isomerism here. Look at the compounds, try to write down the structures. Okay, Sujal Patel, you answered as 6, that means you mean all the 6 compounds exhibit geometrical isomerism, is it? So, what are other answers, guys? Right, here all the 6 compounds are going to exhibit cis-trans isomerism. Look at the compound structures. Each and every complex, right, every complex exhibits cis-trans isomerism. Is that clear? Is that clear to all of you? Do you have any queries in this? So, we have come to the end of the session, and from the next session onwards we are going to start with the organic chemistry. Okay, the next almost 5 to 6 sessions will be completely focused on the organic chemistry, the previous questions, mainly the approach, how to answer the questions and how to save the time, and the tricky ways, like where in which you have to study the organic chemistry, because organic is something like you need to have a thorough knowledge on all the chapters. You cannot skip any functional group also in order to solve any question, because the conversions are ranging from one chapter to another chapter, right. Those are the questions which we have be discussing from tomorrow onwards in the organic chemistry. So, till that I am signing off, guys. Thank you.